Hey everybody, this is problem number 7 on practice exam 3-1 in the fall 2021 semester in Chem 1211. And the question is, how many unpaired electrons are there in the ground state electron configuration of a nickel 2+ ion? So this is an electron configuration problem. We're interested in the configuration of a heavy atom ion. But it comes with a couple of extra wrinkles. First of all, we're dealing with a cation, and that is definitely worth noting here. And second of all, we're dealing with a transition metal, and that's also worth noting as we're going to be in the D subshell, and that's going to create some interesting conceptual issues with the electron configuration. So how do we proceed here? Well, electron configuration of an atom, I encourage you to use the periodic table and make sure you can read or get a start on reading electron configurations off of a periodic table for the exam. Nickels right here, and this is a good place to start. What row am I in? First of all, I'm in row 4. And I know that the core of a nickel atom includes all of the electrons up to argon. And so to start things off, I can say that the electron configuration of nickel 2+, which hasn't lost any core electrons, which is normal for stable cations, is going to include all of the electrons of argon in their corresponding shells, subshells, etc., and start there. I may also start by thinking about the electrons in the 4s subshell and thinking, for example, about 4s2, 2 electrons in the 4s subshell, and 1, 2, 3, 4, 5, 6, 7, 8 electrons in the 3d subshell for a neutral nickel atom. And let's actually write that down separately. So for a neutral nickel atom, we'd be looking at all of those electrons in argon, 4s2, 3d8 would be the electron configuration of a neutral nickel atom, right? Just naively proceeding across the periodic table. Now, what happens when a transition metal atom loses electrons? Remember that those energy levels jiggle. So a level that was higher in energy, the 3d subshell, can dip below the 4s subshell in energy, and that's exactly what happens for transition metal cations. As soon as they lose an electron, the energy of the 3d subshell goes down quite a bit relative to 4s and becomes lower in energy than the 4s. And this has to do with the fact that the 3d orbitals, or electrons in the 3d orbitals, are actually on average closer to the nucleus than 4s electrons. And so as the effective nuclear charge of the valence shell goes up, those 3d electrons decrease in energy faster than the 4s electrons. So that's a long-winded way of saying that in order to proceed in going from neutral nickel to nickel 2+, we're going to lose both of the 4s electrons. And we're going to lose 2 electrons because the charge of the ion we're interested in is nickel 2+, and both of those electrons come from the 4s subshell. If we only lost 1 electron, actually the same idea would apply, and we would take that remaining 4s electron and put it down now, because the 3d level is below the 4s in energy, into a 3d orbital, leading to a 3d9 configuration. In this case, we're going to lose both of those electrons and in the 4s subshell and go straight to a 3d8 situation. Now, in terms of actually answering the problem, how many unpaired electrons are present in the ground state electron configuration of a nickel 2+ ion? Let's get an orbital energy diagram down to unpack this. So energy on the y-axis, and actually to illustrate a point that I made earlier, just waving my hands around, in the cation, the 3d subshell is lower in energy than the 4s subshell. I know I've got 8 valence electrons based on nickel 2+, based on the number of electrons in a nickel 2+ ion, and I'm just going to start filling the 3d subshell with those 8 electrons in accordance with the Aufbau principle and Hund's rule. So 1, 2, 3, 4, 5, 6, 7, 8, and I'm realizing that I have missed an orbital in the 3D subshell. It's got 5, not 4. And if my math is serving me correctly here, we're going to need to take one of those electrons and put it there. You know what? Let's just start over because I want to illustrate Hund's rule in action as you're filling electrons into d orbitals. The first 5 electrons will all go into unique orbitals within the 3D subshell, like so. And then to finish this off, we're going to do 6, 7, 8, pairing those last 3 electrons. How many unpaired electrons do I have left in this configuration? 2. 2 unpaired electrons in a nickel 2+ cation.